So this is example number 1 for power screws. In this particular example, we are not so much interested to know if your thread or your screw will be strength-wise possible. We care more of the mechanics of the power of the screw. We want to make sure, we want to know if it's going to have the correct efficiency, what's going to be, if it can, efficiency is the main goal. We want to know the loads. We want to know what really happens with this power screw. And what's very interesting in the problem is this power screw is cyclically raising. Uh, so what it's doing is you have something that's actually, you have the screw that's actually lifting cyclically a load that goes from 2,000 pounds to 5,500 pounds. Okay, and this is as we go with time. Okay, so when this is happening, you don't want this to lock in at a moment. You want this to completely going up and down. So you know that. So one thing that we can say is in cycling mode, we want no self-locking. Okay. So if you don't want self-locking, the screw must overhaul. Okay, so that's what we know that has to happen. Okay, so that's one thing that you have to take care of. And then also, you know, the rate in which this is displacing. So the rate in which, if you have the screw and the screw is going up and down, it's actually moving at this rate. It's moving at 3 inches per second. Okay, we will work with this later. Now, it says use a standard AMC thread for the triple start. If it says triple start, you already know that L is equal to N, your lead is equal to this. So in this problem, N is equal to 3. That means your lead is equal to 3 times the pitch. Okay, so we want to work with a modified thread. So modified square thread with a thread angle of 5 degrees. So that means that alpha is equal to 5 degrees. So if you look at the chart I gave you in class in my handouts, the case that we are working with is the modified squared. And you can see that this is 5 degrees. So this is the case that we are working on. You can still use the same equations for squared. It's just slightly modifying it only. This is not a AMC standard ACME power screw. This is a modified square power screw. Okay. The other thing that the problem says, the screw and sculler are oil lubricated and assume steel is a hard steel. Why that information is given to us, before I move on, this is the table for ACME threads. So any diameter I'm going to choose has to come from this table. Okay, so and that's given in your notes. The handout I gave you in table 8.3. This is not in your textbook. So to find the lubrication constants here, now you have to watch out. So when I'm going to do the problem, I'm going to have a problem first when the problem starts, right? When you start going up or you start going down, suppose that you want to stop the problem, okay? And then the other problem is when you're running. You got two issues here, okay? And for start, I want to know what is the coefficient of friction of my thread and my coefficient of friction of my collar. Same thing here. What is coefficient of my thread and my coefficient of friction of my collar? Okay, so let's go with the running first. I have thrust collar coefficient. This is hard steel on bronze. So at start, this is 0.08. So this will go here, 0.08. And at running, it's 0.06. So this will go 0.06. And then when it starts, this is the case of steel on bronze, right? That's the nut that we are using. So I'm going to assume that the highest possible value is going to be to my start, and my smallest value then I will use for my running. Okay, this is an assumption, lack of any other information, that's what we will be using. Okay, steel on bronze, that's what we are working on. Okay, so the next thing I can do is, I know the condition for overhaul. The condition overhaul says that lower A has to be less or equal than 0. And from here, we showed in class in your handouts that this has to be less than your lead, pi, your mean diameter cosine of alpha. Okay. Then from here, I can rewrite this in the following form. Divide by cosine of alpha has to be less or equal than L over D, dm. So why do I do this? Because this is all a constant. This is known in my problem. This is not going to change as my diameter changes. If my diameter changes, these two things are going to change, because as you can see, as my diameter changes, my pitch changes, right? So if my pitch is going to change, that means that my lead is going to change. So just remember L is equal to, this is equal to 3 times P. So this is a number which we already know. So I can replace everything in here. And so this will be pi. And this will give me pi 0.16 divided by cosine of 5 degrees, less or equal than L over dm. Okay, so from here, we find that L over dm has to be bigger or equal than 0.4245. So this is the condition that I need to satisfy in this problem to make sure that it will overhaul. Okay, so let's go and start with the initial guess. And this is an arbitrary guess. We don't know if this is going to work or not, but we will start somewhere. So I'm going to choose this gauge right here. This is the diameter I decided to use. So for this diameter, you can see that D is equal to 1.75 inches. You can see that your pitch is equal to 1 over 4. So let's go ahead and see what happens. So your diameter is equal to 1.75 inches. Your pitch is equal to 0.25 inches. Your lead is equal to 3 times P, and that will give you 0.75 inches. And your pitch diameter or your mean diameter, remember they're all the same. So your pitch diameter is 1.625. This is 1.625. This comes from your table. And then let's go and check the overhaul condition. That's the condition I really care for. So in this case, L over dm, that would be 0.75 divided by 1.625. This gives me 0.46, and you can see that this is not bigger or equal than 504. Okay, so that means I need to take another diameter. So I'm going to go back to my list, and I'm going to say, okay, that one did not work. Let me go one up and see what happens. So that's the one I'm going to use next. And then you use this, and you say, well, a diameter is 1.5. Your pitch is 0.25 as well. Look at the problem. This is 4, so it's 0.25, 0.25, and this is 1.37. So your lead will be 3 times pitch. This gives you 0.75 inches. Your mean or pitch diameter will be 1.375 inches. And if I check this condition now, L over dm, that gives me 0.75 divided by 1.375. This gives me 0.545. This is bigger than 0.504. So therefore, this is completely acceptable. Okay. So now that I can rely on this, uh, configuration that actually indeed it will overhaul, then I'm going to start actually doing the rest of the evaluation of the problem. Okay, so what the problem is telling you, I need all the configuration, and that's going to come from this table. So this was the diameter I'm going to use. So from here, you have the D in the problem. D is equal to 1.5. Your pitch is equal to 0.25 inches. Your threads per inch is equal to 4. Your lead, remember, was 3 times P because it was triple start. Remember, if it's not triple start, then you have to change this number. Correspondingly, they're 0.75 inches. And your pitch diameter is given right here, 1.375 inches. Your root diameter is a minor diameter, that's this one right here, 1.250 inches. Your alpha is equal to 5, that was given in the problem, and is for the modified squared ACME screw. And one thing that you have to keep in mind that your DC, this is typically given is 1 point times D. This is standard, okay? If this, your diameter of your collar is not given, this is the equation that you're gonna use for, to find that. Okay, so this is very, very important. Many times it's not given and lack of information, that's what you will use. Okay, so now let's analyze the screw mechanics. Okay, for screw mechanics, note that I am not applying a factor of safety here. I don't need to apply one. This is equal to F max. Gives me 2,500 pounds. Okay, I'm going to start. This is a start, by the way. This is start. This is what happens when I start everything. So your friction is 0.16. At start, this is 0.08. Remember, we found all these values here, so this is the values I'm going to use. Then your so you got two. First, you got the screw and nut interface. That is TRA. That gives you FDM divided by 2 L cosine of alpha plus mu F pi dm, everything divided by pi dm cosine of alpha minus mu F L. And I have everything, right? I got my mean diameter, I got my lead, this is 5 degrees, I got my coefficients, I got everything. If you replace that, you will find that you get 595 inches pound. Then this is just a screw nut interface. You need to find also the truss collar contribution. Okay, that would be TRB is equal to MC DC divided by 2. So I have all these quantities here replaced, and I find this is 175 inches pound. So at the end, at start, when I start my journey, my total torque to rise will be RA plus RAB. You're going to add the both contributions, and that gives you 778.45 inches pound. Okay, this is what happens when I rise. Now, when I am at run, so now you didn't start, you're just cyclically moving. Remember, this is a cyclic problem. So what happens not at the start, but everywhere else, not at this location right here. So you go from here to here, everything that happens there when it starts, before it starts. Okay, so at run, we're going to call this at run. What you're going to have is F max will be 2,500 pounds. Mu F is equal to 0.10. Mu C will be 0.06. And then screw nut interface will be TRA. And you can see it's going to be the same equation that I had before. The only thing that's going to change is the value of my coefficient of frictions. Everything else should remain identically the same. So this value is going to change. This is not going to change. This is all going to remain the same. These are properties of my, the geometric properties of the screw I chose. Okay, so if I replace all the values, I find this gives me 479.30 inches pound. Okay, now the thrust color contribution will give me TRB will be mu C FDC divided by 2. That gives me 140.63 inches pound. Okay, and then the total contribution of TR at running would be TRA plus TRB would be 619.92 inches pound. Okay, so this is all at rise. I have to repeat the problem again and see what happens when we are actually what really happens when we are at lowering. Okay, so we did that rise. Now we will do torque at lowering. Okay, torque at lowering, what you want to do is first again at start, you do at start, and then you do you will do at start, and then you will do at running. Okay, so at lowering has the same friction. The friction coefficients don't change. What's going to change is the screw nut interface. The equation is going to change for lowering. The lowering equation is different. So TLA lowering would be FDM divided by 2 mu F pi dm minus L cosine of alpha pi dm cosine of alpha plus mu FL. Okay, so if I replace all the values here, I find this is minus 21.76 inch pound. Okay, and then the fact that this is giving negative, that was by definition and by design, because I want this to overhaul, okay, and not self-lock. Okay, since I designed it for overhaul and self-lock, and I designed it such that it would be less or equal than 0, that's why you're getting negative, which we kind of expected, but that's how we designed it. And the next thing is your thrust color contribution will be lower. We call this B, will be mu C FDC divided by 2. Replace all the values, gives you 87.5 inches pounds. So the total contribution at start, when you want to start to lower, will be TL, will be TLA plus TLB, and that will give you 165.72 inches pound. Okay, now we have to repeat the problem again, but for run. Okay, so let's do this again. At run, I'm going to have F is equal to F max, 2,500 pound, and I want to have MF is equal to 0.10, 0.06. Then this will be the screw nut interface. Will give you TLA dm over 2 mu f pi dm minus L cosine alpha pi dm cosine alpha plus mu f L. This gives you minus 123.78 inches pound. Also, you can see that even at the run, when you're lowering, gives you 0. Again, this is because it is overhaul. Okay, that's what it really means. Okay. Then the next contribution is the thrust color contribution. That tells you when you lower, it's going to equal to mu c FDC divided by 2, and that gives you 140 25 inches pounds. And the total torque to lower would be TLA plus TLB. That gives you 16.90 inches pound. Okay, so the question and the next question would be, does the spring self-lock or overhaul? We know it's going to overhaul because we designed it as such, right? So then the question now is, what is the efficiency? So to do the efficiency, for discussion for the efficiency, what happens if I have the collar effect? Okay. For the collar effect, your E is equal to FL 2 times pi and your total torque to rise. Okay. So just remember, this is 2,500. This is 0.75. This is 2 times pi. And the value that we're going to use is this a start 778. So 778, and that would give you 0.383. So this is the color. Let me do this problem. What happens if I did not have color? This is just to show you and compare. So if I didn't have the color, what I want to do is I want to eliminate the thrust color effect, right? So if you go back, I had this is the thrust color. So I'm not going to include this. This is a screw nut effect alone, and let's see what happens. So if you evaluate this, you get this value. So you're basically saying is that your color if you can see, reduces your efficiency. It reduces your efficiency by 13.69%. And this is very typical. Sometimes you need color, but you're going to pay a penalty price for that. You're going to lose your efficiency of your problem. Okay. Now, the very last question in this problem is, what is the minimum power and torque requirement for a driver motor? So let's suppose I have a driver motor and I would like to replace all this with a driver. And my question for you is, how much would be, what should be the minimum requirement for that engine, right? The small motor that we're going to use. So for that, I know that your minimum T has to be the biggest value that you have among all these values. And the biggest value I'm going to have when I'm rising, the 778. So what I'm saying is this has to be bigger than this value for this to actually, for the driver to be effective. So one of the things I can do then is I need to find my RPMs, and your RPM is actually going to give you by this equation. This is given by your velocity over your lead. So velocity x dot over your lead, okay? And what I had in the problem was this is 60 seconds per minute. This is where the 60 comes from. And this is 30 inches second, okay? And what I know is this is going to give me 0.75 inches in one revolution, one full turn. So this gives me an RPM of 240 RPM, okay? So if that's the case, then the horsepower that I need in my problem is given by this equation for your driver, and that would be 77845 multiplied by 7 multiplied by 240 divided by 63025, and that gives me a value of 2.96 HP. So your engine needs to have HP of 3 horsepower or more. That's the minimum requirement for your engine. So this kind of summarizes what we really want to do with our power screws. As you can see, is I am interested in knowing, let me summarize a few things here. So first you want all the geometry, right? You want to choose, find the geometry, choose your screw geometry that you're going to use. Then secondly, you want to find what your torque to rise and at run, at low, at start, and also find your torque to lower at run and at start. And then you want to find the efficiency, okay, FL 2 pi TR. And you could also compare this if you wanted to with 2 pi TRA. This is no color, this is with color. And then the last thing you want to recommend is how many horsepower does your problem have for a driver. So these are like 4 things that you basically are looking for in these problems. So this will conclude example number 1.